as a rush of hypervelocity gases.
It's a nuclear pogo stick in space. It's time for some more real engineering. Specifically, Project Orion, or Earth to Mars in 10 days. So is it a one-way trip? Those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer, a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge.
70 years ago, we found the key to the solar system. It would unlock affordable launches of thousands of tons at a time, rapid travel to all the planets and even beyond the solar system. But we decided not to use it. Nuclear energy. This isn't science fiction. Legitimate, feasible designs were tested and presented by scientists involved in the Manhattan Project in 1946.
Yes, initial designs for this did show up. I believe he's not referring to Project Orion itself, but he's referring to the Stanislaw Ulam and Cornelius Everett papers in 1946 and 1947. The Orion program itself was thought of in the 1950s.
Their work had started in secret and first revealed to the world as a tool of terrifying destruction. Now they were eager to show off its peaceful purposes. Their plans would solve one of the greatest problems facing the rocket industry, the rocket equation. The equation that demanded chemical rockets to become massive stacks of fuel with huge expensive sections being discarded into the sea.
Yeah, not the most energy efficient way to get into space.
Nuclear energy could solve a lot of this problem, but not through nuclear reactors providing thermal power to exhaust gases. This would be like drinking from a swimming pool through a straw.
So on that note, nuclear thermal rockets, their main limitations are going to be propellant temperature and chamber pressure. Once in space, they can theoretically achieve roughly twice the impulse from chemical rockets, but they don't have the thrust-to-weight ratio necessary for direct ground launch. This is the inside of a tokamak, not sure what that's doing here.
Efficient, but without the thrust needed to get large payloads off the ground.
Yeah.
The world had witnessed the immense power nuclear bombs could deliver in an instant, equivalent to tens of thousands of tons of chemical fuel in a much smaller package. If these explosions could be harnessed for a rocket, they would transform how we got to space. But the only way to get a vehicle moving with nuclear explosions was to place it inside the fireball of an atom bomb.
I get he's going for a colorful metaphor here, but Orion, or any iteration of it, is not inside the fireball. The pulse unit is going to detonate tens of meters behind the pusher plate when we get into that.
Most people today would assume everything is simply destroyed inside the Hellfire and leave the insane idea at that. Scientists in the 50s had a different approach. It
is more destructive than chemical weapons, so sure.
Is how Project Orion was born, and this is its story. The first question the engineers and scientists...
Kind of a funny looking artist rendition of it, I appreciate that. A space piston using nuclear impulses.
Behind Project Orion had to answer was what can survive a nuclear blast. The US military was very interested in this question.
Specifically the blast, the shock wave, not the actual fireball itself.
They needed to know how to build shelters to resist a nuclear attack, and in turn, how powerful their warheads needed to be to destroy hardened targets. The heat, radiation, and shockwave from a detonating nuke could destroy the other nukes in a volley too, so knowing how closely they could be spaced was vital.
That is true. Not like what you see in video games of a nuclear bomb going off and then setting off the other nuclear bomb to create two nuclear explosions. Nah. If one of the bombs is going off, it's just going to destroy the other nuclear weapon.
Answers would come from the many nuclear tests they were eagerly conducting. Specifically, the experiments that involved placing different materials at varying distances from ground zero of a nuclear device. One such experiment involved Lou Allen's balls. Lou Allen was an Air Force physicist who was worried about America's supply of tritium, a heavy isotope of hydrogen necessary to fill thermonuclear warheads.
So thermonuclear, you mentioned atom bombs earlier that are pure fission weapons. Thermonuclear bomb involves a fusion stage, which is why the tritium is used.
The first fusion bomb was detonated in 1952's Ivy Mike test, and it was quickly followed by plans for warheads of much larger yields, into the megatons, which needed more tritium. Alan knew lithium could transform into tritium after being bombarded by neutrons, and the radiation of a uranium fission bomb could do the job.
Hence adding that into your fusion stage. And yeah, the fission part's going to create a massive amount of neutron flux to get that second stage going.
So, he had these balls blasted by a 20 kiloton yield device to test that theory. Experiment Viper took 1 meter wide steel spheres filled with a lithium-containing material and placed them just 10 meters from the point of detonation of an atom bomb. The spheres would absorb the intense radiation without being destroyed, thanks to a graphite coating. Graphite was used because it has the highest vaporization energy for its weight of any solid material.
So graphite ablation does provide a transient protective plasma layer, but survivability is also going to depend on distance and yield scaling laws, such as the cube root law of blast radius,
allowing it to absorb a huge amount of heat energy before becoming a gas, which is why it is so commonly used in ablative heat shields. But two surprising discoveries were made as a direct result of these experiments. First, they discovered that when the balls were engulfed by the thermal blast of the warheads, a millimeters thick layer of graphite vaporized into a protective gas shield, allowing the spheres to withstand a 150,000 degree fireball without damage.
So that 150,000 Celsius number is derived from early X-ray brightness. That's in for the order of microseconds, not the bulk gas temperature as far as what the outside air is. It doesn't stay 150,000 C for long. If it did, then yeah, it's going to overheat.
And second, the spheres had been shot out of the fireball like cannonballs by the expansion of that gas. What if this phenomenon could be harnessed for a rocket? The idea didn't get much traction. That was until Sputnik sailed over the United States in 1957, kicking off the space race. Vast resources were quickly unlocked to fund efforts that would beat the Soviets in space, now and in the future, including less certain technologies with great promise. The Advanced Research Projects Agency was set up in early 1956.
This is cool. It kind of has a retro-futuristic vibe, but with a lot of challenges.
Project Orion began under the same year. Papers detailing the physics of the principle became workable designs and larger concept spaceships began to be planned. But Project Orion wasn't just sketches. Actual designs began to be tested, including a small rocket that was pushed to 100 meters in altitude by 6 explosive blasts. Another was a scale model that was exposed.
Yeah, start off making it small as a proof of concept. That's the sound principle.
2 repeated shock tests. Several spaceship designs of various sizes and purposes were drawn up, ranging from lunar Orions that went to the moon to 10,000-ton Orion ultra-heavy lift vehicles.
Orbital battleship. Jupiter shuttle, interesting.
That carry their own weight into orbit with each launch. Each one would be a massive step ahead of the spacecraft of their time and still remain unmatched to this day, capable of crossing the entire solar system in a month or heading to Alpha Centauri in a human lifetime.
Okay, as proof of concepts, sure. Going that kind of distance works on paper, and I think this is where the Mars in 10 days comes from. I've heard of this claim before, and that's based on really large designs, such as the crazy battleship-shaped object that he just showed a picture of. Not to mention optimistic pulse cadence with a gigaton scale energy budget, so 1,000 megaton plus as far as your payload on this thing, which would make it far larger than any nuclear arsenal in one location that's small. You're going to have unrealistically high delta Vs for said mission, and I think we're looking at theoretical maximum exhaust profiles. I'm not even going to entertain the Alpha Centauri one, but for the Earth to Mars in 10 day, you're going to need about 150 to 200 kilometers per second total delta V, which is at least 3 times higher than the most optimistic Orion numbers I've ever heard of, with several kiloton individual pulses. This ship wouldn't be manned, by the way, for obvious reasons. And that's going to figure out to about 5 tons of TNT per kilogram of payload. So thousands of kiloton pulses. very high neutron and gamma dose, which, okay, it's unmanned, but still, neutron dose is going to embrittle your vessel. A much faster cadence, a faster pace, so any collision with space dust is going to be more devastating. So, not terribly realistic. I would say a manned Orion vessel could probably cut a Mars trip from 8 months to, say, 1 to 3 with aggressive trajectories. And you might be able to do an uncrewed one in just under 30 days, which is incidentally about the time of a reasonably fast refueling outage at a nuclear plant. After all, for uncrewed, you don't have to worry about life support. But that's speculative, because the rule of thumb you're working with here is energy requirements are going to scale with the square of velocity. Going 4 times faster, they're going to need 16 times the pulse energy. So if Project Orion worked, it absolutely would have shortened the trip to Mars, but not to 10 days.
But for the sake of this video, we will focus on one specific design, the 4,000-ton Orion ship, the first serious proposal from the project. It was to be a heavy lifter, a 78-meter tall bullet.
That's a ridiculous big one. It's not as crazy as some of the other proposed ones, probably the one that he mentioned about Alpha Centauri. But yeah, that's a big spacecraft.
Able to deliver 1,115 tons into low Earth orbit, but also capable of delivering 300 tons to Mars and returning without refueling. Docking in space had not yet been attempted, so being able to send up whole space stations in one piece or perform entire missions with one vehicle.
Talk about seriously putting the cart before the horse. Yes, that's true. This is the 1950s. Nobody's ever space docked anything yet. Just sending satellites.
Was a distinct advantage. Declassified reports tell us how it would have worked, focusing on 4 critical elements. The first and most important element is the nuclear devices that would propel the spaceship. It couldn't be just any design. It had to be both small and powerful. Both the United States and the Soviet Union were trying to compete by building the biggest and most powerful weapons possible.
I mean, if you're talking small and powerful, nuclear is the best technology we got.
But scaling up nuclear bombs is easy. Trying to make them work effectively at a small scale is much more difficult. Neutrons are needed to sustain a nuclear chain reaction, but they are highly penetrating and quickly leak out of an atom bomb. Smaller cores let go of more neutrons, so fewer fission reactions happen inside and much of its fuel is wasted. But this can be compensated for with higher explosive compression to increase density.
Yeah, the very first nuclear weapon, Little Boy, had an efficiency that was less than 5%. If you're talking about the actual fuel used, that was a different sort of design, but still, similar concept.
And thereby increasing the chances of neutron collisions. But that comes with its own design challenges. The US was obsessed with inventing miniature warheads to fit on a new generation of submarine-launched ballistic missiles, to arm a new branch of the United States nuclear arsenal.
That was cutting edge back then, too. It's interesting how old this idea is, and it's still somewhat sci-fi, but sub-launched nuclear weapons are by no means cutting edge today.
The key was plutonium, a more volatile fuel than uranium, encased in beryllium that efficiently recycled and reflected neutrons. This was even used to create the Davy Crockett tactical nuke, designed to be launched by soldiers on the battlefield.
Yes.
This approach...
That right there, if you're familiar with the video game Fallout, the Fat Man nuclear catapult launcher that you get in that game is loosely based off of that weapon, and every bit as silly.
Was perfectly suited to Project Orion's needs, and they quickly adapted the idea into the miniaturized nuclear bombs that would be lobbed behind the rocket, and they dubbed them pulse units. These pulse units would weigh about 1 ton each and release 25,000 tons worth of TNT. Half of the pulse unit mass, however, was a plate of tungsten. That plate was the difference between a bomb and a rocket engine.
So that's right as far as the concept is concerned. Per shot, I mean, when you get down to individual pulse units, smaller on the order of 0.5 to 1 kiloton, which is comparable to tactical nukes you see today. And the beryllium is going to act as a neutron reflector / tamper. And from what I've heard, they kind of stopped at calling them bombs because it's obviously politically loaded. But That's why the team proposed 1-point safe designs, where they were subcritical designs until they actually imploded and provided their pulse. Interesting.
We know that nuclear bombs create intensely hot fireballs that rise off the ground as menacing mushroom clouds. But the actual output of a fission reaction is lots of X-rays, fast-moving neutrons, and a thin burst of plasma.
And fission products, that's the nuclear waste that is of the largest concern within a nuclear power plant. A lot of it decays away quickly, but stuff like cesium-137 and strontium-90 with a half-life of 30 years, that's the stuff in the spent fuel that sticks around. But in the context of a nuclear weapon, it's all just blown out. Talking about an explosion on Earth is just going to be blown out, super diluted in the atmosphere, and it's just carried around in the form of fallout. As far as how severe it is, well, it depends how close you are to the explosion, and it depends on the weather, which way the wind's blowing, as far as what kind of dose you're going to get. Though a lot of it, the vast majority of the radiation of the radioisotopes will decay away within the first 3 days.
Its atmosphere absorbs them within a few meters and turns them into heat. That's how the mushroom cloud is formed, as the heat rises and cools.
Note that mushroom clouds are by no means unique to nuclear weapons. Any high-yield device, anything with a high enough yield is going to produce a mushroom cloud. It's just good old-fashioned Archimedes principle buoyancy in air. Setting off a massive propane repository million-gallon tank would do it.
In a vacuum, an atom bomb just looks like a flashbulb burning out. A mere spark followed by an invisible wave of radiation. Still deadly, but useless for moving things in space.
What he means deadly is if you're close to it, yeah, you're still going to get a high neutron dose, high gamma dose.
A thick plate is added to the pulse unit to intercept the energy of the fission reaction, absorb it as heat, and explode out as a rush of hypervelocity gases.
It's a nuclear pogo stick in space.
It is those gases that act like the exhaust of a rocket engine to propel the vessel in a vacuum. Tungsten was chosen because it did an excellent job of stopping harmful radiation.
Tungsten is an excellent radiation shield, even more effective than lead. Lead is more commonly used on Earth because it's more cost effective, but in space, where every little bit of space counts for using your material, yeah, tungsten, you're going to be better off with that. Now, tungsten is primarily a high Z, that is to say, high atomic number, things with a lot of protons in the nucleus, in addition to being shielding. And the X-rays ablate the tungsten surface into plasma, which is going to expand at 100 kilometers per second. So that momentum is going to impart the thrust. And radiation shielding of the crew is also handled by the propellant tanks and the shielding, referred to as shadow shields, not just the pusher plate by itself.
Reaching the spaceship while being 10 times more compact than graphite. Project Orion's engineers also conceived of a way to channel the energy of a nuclear device so it would preferentially strike the tungsten plate rather than dispersing in all directions.
Yes.
A cone of beryllium oxide encased in uranium was able to absorb the initial release of energy from the nuclear reaction.
Basically a flow reducer, but just like a flow reducers in pipes, except you're not talking about fluids, you're talking about radioactive propellant.
The instant expansion of the beryllium generated a shockwave, and using techniques already known to engineers for how to turn explosives into shaped charges, like the anti-tank heat warheads, it could be redirected to push against the tungsten plate.
And using principles they learned from the Manhattan Project with how to steer neutrons, high-energy radiation. But yeah, combining a couple of disciplines, which is cool.
With all inefficiencies accounted for, the pulse units would have an exhaust velocity of 36,000 meters per second, 10 times the exhaust velocity.
Power of 100 terawatts. So power, it gets kind of funny because 100 terawatts is a ridiculous number. To give you a sense of scale, 30,000 terawatt hours was all of the energy produced in the world in 2024. But power is just energy per unit time. And in the context of nuclear weapons, you're dividing by a really small number. on the order of microseconds to get this big inflated number. So yes, that if you're going to use a number like power in the context of setting off a bunch of small nukes, then yes, you're going to get big numbers, but the amount of time that the energy is going to be going is limited, hence the pulsing motion. It's kind of similar how pulse lasers designed to remove tattoos can get numbers in the megawatts, but you're not putting sustained megawatt heat input on your skin. That would really ruin your day.
Of a conventional chemical rocket. The pulse units would be detonated roughly once per second, releasing an average of 100 terawatts of instantaneous power.
Okay, keyword instantaneous power, not sustained power that you see on a nuclear power plant, for instance, or even on a chemical rocket. So you're not exactly comparing apples to apples here, but yes, this pulse, the velocity numbers make a little bit more sense as far as comparison, but you get the idea. This is way more energy dense than chemical rockets.
That's 5 times more power than all of humanity uses at any one moment today.
Yes, but it's in spikes.
But the engine's thrust was delivered in millisecond pulses, like hammer blows. While Project Orion's experiments did prove that a solidly built vessel could handle such jolts many times, some accommodations would be needed for a crewed Orion ship. A suspension system was the second vital element they designed. Facing the nuclear blasts was a 26-meter diameter steel disc coated in oil. Tungsten gases from the pulse units bounced off this pusher plate to transfer their momentum, while the oil acted as a sacrificial layer that prevented damage, a technique actually shown to work in real atomic tests. The pusher plate would then get violently slammed backwards into a gas bag. Like an airbag during a car crash, this bag would reduce the plate's acceleration from thousands of Gs to a few hundred Gs, which is still enough to crush a human instantly. So then, a 27-meter long suspension arm that contained springs and hydraulic pistons smoothened out and delayed the pushes into an average shove of 1.25 G.
I mean, that logic is sound, though again, we're based on estimates here, just like everything else. The real Orion tests did show a 2-stage shock absorber could indeed reduce a millisecond impulse to a gentle rise. So yeah, this part's actually plausible.
If everything worked out, it would be about as bumpy as driving down a country road. The gas bag and pusher plate kept on wobbling while the suspension arms moved through their cycle.
Yeah, 1.25 Gs isn't very much.
Running down the center of the suspension arms was a pneumatic gun that shot the pulse units through the pusher plate every second, with a shutter closing behind the pulse units each time to protect it from the hypervelocity tungsten plasma moments away from hitting it. Finally, there was a question of storing the pulse units. Engineers settled on disc-shaped magazines, each holding 60 pulse units in ammo drums feeding into a delivery system.
That's kind of funny. Belt-fed nuclear weapons. Just Metal Gear.
Adding Delta V to the Orion spaceship was a simple matter of stacking more magazines. Reaching orbit would consume nearly 600 pulse units, while a full mission to Mars...
I keep forgetting they actually intended to launch this thing into orbit, setting off a bunch of nukes in the atmosphere. Yeah, you're gonna bust a whole bunch of treaties. Well, I guess they didn't exist in the 1950s yet, but that's not even remotely a good idea, because if this experiences any sort of failure, you want this thing with payload of nuclear weapons to come crashing down into who knows where, and be recovered by who knows who.
With return would need 1,500. But it was because of this final element that Project Orion fell apart, not because its design was flawed. Project Orion was, in a sense, radioactive. It was pretty sound.
In every sense, radioactive, I would add.
From an engineering perspective, and offered a ridiculously huge step forward in terms of spaceflight capability. But from a bureaucratic perspective, it was impossible to sustain. In mid-1958, NASA was founded to take responsibility.
Maybe a space-only craft, but setting these things off in the atmosphere, plus the jerky motion of that within the Earth? No.
Over spaceflight development from ARPA, which meant it took over Project Orion too. It took less than a year for NASA to decide it didn't want to deal with the secrecy and complications of handling nuclear explosives technology. So, it cut funding to Project Orion in 1959. It didn't.
So, Like I said, if this thing was to fail, it could scatter radioactive material. Even sub-kiloton bursts would release EMPs in the upper atmosphere that could damage satellites. And a launch pad abort with hundreds of these subcritical but fissile pulse units, while it would not result in, say, a nuclear explosion at the launch site, it would create some localized plutonium contamination. So I can totally understand why you wouldn't go with this sort of thing if you're going to launch it into space from this. You'd have to make your starting point already in orbit.
It helped that NASA was in the process of investing billions of dollars into the creation of the Saturn family of giant chemical rockets to land on the moon. Project Orion was going to make all of that effort obsolete as soon as their work was done. One 4,000-ton Orion launch would match,
or at least provide an alternative means of getting there,
the total mass lifted into orbit by all of the Apollo launches. So, Orion was shopped to the Department of Defense as a project with military potential, capable of lifting an entire battleship full of ballistic missiles into space with no counter threat. Needless to say, it caught their attention. This was enough.
Those like battleship guns and little pods, missiles? Alright, now we're getting into some SDI Star Wars, not to be confused with the Star Wars movie franchise.
Justification for funding Project Orion for 5 more years. During this period, the prospect of actually building and testing an Orion spaceship slipped away further. It became clear that a ground-launched Orion was no longer politically acceptable, as the public became aware of the fallout of all that nuclear weapon testing and would not realistically accept a launch vehicle that took off with hundreds of nukes over their heads.
I don't see what engineer would be accepting of just the risk associated with this. I mean, I get back in the 1950s, it was a different time, but especially today, just the risks of something like this from the ground, it doesn't seem consistent with a healthy nuclear safety culture.
The project's engineers were forced to design much more modest vehicles that were light enough to be placed on a chemical booster, so it could be lifted up to a 76-kilometer altitude before starting its nuclear pulse cycle. The idea was that any fallout from the nuclear explosions would be dispersed harmlessly, with the majority leaving Earth entirely. But this obviously wasn't
that could still mess with satellites at that elevation.
Terribly safe either. A full safety study was conducted. It found that high-altitude detonations would produce significant electromagnetic pulses, strong enough to knock out nearby satellites. Risks like an early pulse detonation destroying the ship's pusher plate or a misfire leaving the suspension cycle out of sync were also highlighted. A fully loaded Orion exploding on the launch pad was a terrible possibility too. The worst-case scenario, however, would be a failure during the climb to orbit. A nuclear chain reaction wouldn't happen, but it was possible to set off the high explosives needed to compress the fissile fuel in each nuclear pulse unit and scatter radioactive material over thousands of kilometers.
Yeah, that's a very real risk with this project.
Addressing these problems drastically cut into the potential performance of an Orion vehicle, while making it much more expensive to launch. Compensating for the less impressive performance of these later designs is perhaps why Project Orion under the US Air Force leaned on the military aspect, leading to some crazy creations. The Emergency Command and Control Orion was a 2,500-ton design sitting in a silo like an ICBM, but it would only be launched in the case of a nuclear war to become a flying NORAD backup. The Doomsday Orion used its payload capacity to place a 1,650-ton thermonuclear weapon.
You're better off just making a space station as to act as your command post, like what GDI had in Command and Conquer. Of course, that ended up being a target in and of itself.
In low Earth orbit. It would have a yield of 8,250 megatons, matching all of the American warheads.
Talk about putting all your eggs in one basket. One basket with a jerky flight mechanism.
Combined, and be able to set a land area larger than France on fire just by detonating in space. Another military version was reportedly presented
that math checks out.
to President Kennedy, only for it to be rejected as horrifying and unnecessary. It's easy to discount these ideas as absolutely batshit insane now, but these were the 50s and 60s, an era when dozens of nuclear tests were being carried out at home and abroad every year.
And look, I'm all for the idea of crazy ideas being put on paper just to entertain them and just to see what they are. It's kind of like during the Manhattan Project, the calculation of would this ignite the atmosphere? Everyone was pretty sure the answer was no, but you're going to go ahead and do it anyway. But in the terms of engineering and curiosity, I'm fascinated by ideas like that. I know they'd never be built. There's way too many ethical concerns, and as well as just engineering challenges. Even if you had no ethical concerns, it's more of there's just no way this thing's going to work either. But I still like the idea of bringing them up, and I think it is good. It is healthy to bring up crazy ideas only to see why they wouldn't work, because they could eventually lead to something as to why something completely different might actually work, or be set aside as notes for that can sit and wait for better technology, better supporting technology to come up and move it along, kind of like anything to do with fusion.
Where nuclear reactors were flown on aircraft and nuclear thermal rockets were tested to destruction in open air. Soldiers were watching nuclear explosions from trenches. OSHA didn't even exist yet. Project Orion itself was secret throughout
The Nuclear Regulatory Commission didn't exist yet.
its life, and most details remained classified for decades afterwards. If circumstances were different, it could have gone ahead. It was actually the changing international situation that finally killed Project Orion. The United States,
The Outer Space Treaty,
and the Soviet Union suffered the 1962 Cuban Missile Crisis and started diplomatic talks to prevent a similar escalation from happening again. Part of those diplomatic efforts were mutual agreements to limit where and how nuclear weapons could be tested, culminating in the 1963 Partial Nuclear Test Ban Treaty. Signing it meant that nuclear bombs could no longer be detonated at high altitude or in space.
in addition to underwater testing.
That was the death knell for nuclear pulse propulsion. While the pulse units that propelled an Orion spaceship weren't technically bombs, they looked very similar. Building an Orion, let alone testing it, would mean manufacturing thousands of self-contained nuclear explosives at a time when the world powers were trying to restrain the growth of their warhead stockpiles. Worse, an Orion launch would trigger nuclear attack alarm systems all over the world, and with only the reduced performance of a chemically boosted design to show for it, it was no longer tenable to continue working on it. With that, Project Orion ended in 1965. The dream of a vehicle riding nuclear blasts into space, however, did not disappear. Rocket engineers could not let go of such a massive leap forward in performance. Project Orion veterans tried to keep their dreams alive by showing it off as soon as it was declassified to Arthur C. Clarke and Stanley Kubrick during the early development of 2001: A Space Odyssey, and later by continuing to work on it in their own way. A lot of research has been done on nuclear pulse propulsion since the 60s, accelerated further in recent times by computer simulations that can take the place of forbidden nuclear tests. That has resulted in a fair number of improvements and modifications to the original Orion design. It's widely agreed that no pulse propulsion system should ever detonate nuclear explosions inside the atmosphere. Instead, it should be a vacuum-only vehicle that's delivered into space using conventional launch vehicles. Orbital rendezvous, a tried and tested technique for assembling spacecraft out of smaller pieces, got Apollo to the moon and can be used again to grow a full-sized Orion out of many small launches. Advances in material technology can make it much lighter than estimates from the 60s too, while the latest suspension systems can make the ride smoother and more resistant to misfires. But perhaps the most important innovation, one that can let us imagine reviving Project Orion today, is the way nuclear explosions happen. The original concept for nuclear pulse propulsion used pulse units adapted from small warheads, a near critical mass of plutonium compressed by high explosives. Since then, we have found ways to ignite much smaller amounts of fissiles without using any explosives. The concept is microfission, and it uses tiny fuel pellets, less than 100 grams, compressed magnetically by an external electric field. That current would be delivered by stacks of supercapacitors, coming down superconducting wires and then flowing
This is sounding more like fusion.
across thin transmission lines into the pellets. When this much current passes through a conductor, a strong magnetic field is generated, enough to destructively squeeze the conductor and compress the fuel to ignition. This would release energy equivalent to about 0.01 kilotons of TNT, far smaller than any Orion pulse unit. But the second key new technology is the magnetic nozzle.
Okay, so this is speculative, and this is more of a fusion concept, Z-pinch or inertial confinement fusion style, using fusion pellets with fission triggers or liners. This isn't pure micro fission scale. This is this is really fusion. And this is an extrapolation from where he got that 0.01 kiloton yield from the Z machine at Sandia National Lab. No self-sustaining ignition has ever been demonstrated,
which can catch and redirect the superheated vapor created. With the pulses so slight, a much more modest suspension system can handle them without gas bags or long exposed arms. Even better, the magnetic nozzle has the advantage of being able to extract energy from the exhaust plasma rushing through it, so it can recharge the capacitors ahead of each pulse.
So magnetic nozzles are real for plasma propulsion, but have not captured enough energy for nuclear-grade plasma on this scale. That one's less sci-fi than the little fusion Z-machine sustained pellets. So it's stuff that's experimental, but this is a little bit in the sci-fi territory, I will say. I wouldn't put this in the category of current technology, emerging technology at best.
In 2003, the Minimag concept was actually tested at the Sandia National Laboratory's Z machine, which is able to provide the tens of millions of amps necessary to compress a fuel pellet.
So yes, it can do it, but it hasn't been demonstrated to do it at this scale. Okay, we're closer to it now than we were in the 1950s, if that's the point he's trying to make.
Designers wished to use curium-245 as the fissile fuel, an isotope with an exceedingly small critical mass. But we can imagine a variant using more common uranium-235, perhaps not even at weapons-grade enrichment. A full-scale Minimag Orion spaceship would have had an exhaust velocity 40 times better than any chemical rocket.
This is, again, speculative.
While enjoying 1g acceleration and a delta V on the order of 150 kilometers per second.
So this isn't impossible, is what I will say about this, but this is doing the modern equivalent of what they did back then in the 1950s.
That's enough to get to Mars in 10 days, or reach Jupiter and return in under a year.
Okay, this is a different way I've heard the Mars in 10-day thing. So Mars in less than 2 weeks, theoretically possible, though he's going to need to change his diagram and place Earth and Mars as close to each other as possible for it to work. But actual missions must account for radiation shielding, waste heat rejection, and structural limits on this. So we're going to assume you got some sci-fi materials there that are capable of resisting all this high energy environment. So even with shadow shielding, a crew compartment would need about 10 tons of hydrogen-rich material per square meter to reduce neutron flux to safe levels. You're still going to have thousands of individually certified nuclear devices, which, if you could make them, that's still the proliferation question. There's going to be long-term ablation of repeated plasma impacts on the pusher plate itself. Even with oil or ablative coatings, it just hasn't been tested. But, the physics is sound, the politics not so much. You still have the material and operational challenges, and this Minimag experimentals, and these Minimag technology is still experimental, I would not say it's a near-term technology. And I've always heard it referred to as Z-pinch microfusion. Yes, you're going to have... It has fission triggers, but fusion's going to be doing the business end of the energy creation. But to each their own on terminology. So less sci-fi than other spaceship ideas, but not close. I don't even know if I'm going to put it in the same nuclear fusion 20 years out statement.
Its disadvantages, such as requiring hefty electrical ignition equipment and being unable to operate inside an atmosphere, can actually be construed as safety benefits for a public warier of nuclear energy than ever before. But
never heard someone refer to disadvantages as an advantage, but I guess politics is funny like that.
Is this all enough to revive Orion? Is incredible performance, new safety measures, plus modern improvements enough? There may be one final obstacle. Orion would be a novel, high-performance propulsion system that needs a lot of funding to become real.
Oh yeah.
It would only get that funding from the likes of NASA or the Department of Energy if it met their needs for an intensive high delta V mission. But such mission requirements do not exist because fulfilling them with existing propulsion technology is too difficult. No one is seriously talking about sending astronauts to Jupiter anytime soon, because getting there with chemical rockets is such an enormous task.
By the way, the amount of radiation dose you'd get from there would dwarf anything you'd get on this craft. Jupiter's magnetic field, you might as well be going into a particle accelerator if you're going to be on the surface of Europa.
Which means Orion doesn't have a mission to justify. It's a chicken and egg problem that has trapped many other innovative space technologies, from laser light sails to advanced plasma thrusters. In the long run, technological development in unrelated sectors might get NASA to adopt nuclear pulse propulsion. Perhaps a portion of the resources used to pursue magnetic compression of fusion pellets could be diverted to microfission research, like how progress in making solar panels lightweight and efficient got them to be used in deep.
And that's an interesting point, again, about waiting on supporting technology and using them for supporting technology. As far as Project Orion concerned, I always thought it was a cool idea, but don't do it in the atmosphere, and we need more supporting technology.
Space probes. Or competition in the short term could be the trigger for reviving Orion. It was competition from the Soviet Union that accelerated space development in the first place. And in the future, the United States might look again for technologies that keep it far ahead of countries like China. We can only speculate if or when this happens, and it may take many more decades. But nuclear pulse propulsion
So we're going to say this one's 40 years out instead of the usual 20 years out for fusion-based technology.
remains a massive leap forward, just waiting to happen.
Thanks so much for the recommendations, and thanks so much for watching. I'll see you next time.